Welcome. In this video, we talk about section 7.5, Graphs in Puzzles and Games. The book does spend a good amount of time talking about puzzles, but for us and our discussion, I'm really going to focus on the games part. So we'll talk about graphs in games, stone removal games, and the game of Nim, a classic. Graphs in games. A two-player game is played on the following graph. A penny is placed on a node, and players take turns pushing the penny to a neighboring vertex along a directed edge. The last player who can move wins. So a couple questions come up. So what is the winning strategy? Is there a winning strategy? How do we analyze this? How do we find it out? Perhaps the first thing you notice is that there's one node in particular that looks like the ending node, this D. And if you can push the penny onto that node, if it can be your turn and you push it onto there, that's good. That's really a win because your opponent can push it no further. So let's think of that as the winning node. Here we go, I'll move to a bigger picture. And in general, we want to identify good nodes. So if D is the winning node, it's good, I want to push the penny there, then immediately the three preceding nodes, the C on top, the G, and the J, those are bad nodes because if I pushed it onto one of those, then my opponent could push it onto D and win the game. So those are bad nodes, bad for me. What else can we say? We're sort of working backwards. We're working from right to left. Let's focus on the bottom. How about I? Is I going to be a good node or a bad node? Well, it only leads to bad, so that's actually good for me. I want to push the penny onto node I, because then my opponent has to push it onto a bad node, and so I get to push it onto the good node, and I win the game. How about node F? Good or bad? Well, it only leads to a bad node. So kind of like the same situation down below, that's good. That's good for me. So I want to push it onto F so that my opponent pushes it onto G so that I can push it onto D, and that's good. All right, how about B? Now B is a little bit different. B is a new situation. From B, I can either push it onto a bad node or a good node. So is B itself good or bad? That's bad. So in fact, anything that leads to a good node has to be bad. In fact, so B leads to F, so B is bad, and A leads to F, so A is bad. Can you see that? Let's think about F being good. If my opponent lands on A or B, so the opponent pushes it to A or the opponent pushes it to B, then I'm able to actually take it the next step and push it onto F, which is good because then my opponent pushes onto G and I push it onto D. So I want to be able to push it onto F. I don't want to land on A or B because if I land on A or B, my opponent pushes it to F, and that's terrible. So that's very bad. So A and B, bad. And in general, here's the rule. Any vertices that lead to a good node, those are bad. All right, let's see, what else can we do here to analyze? We have E and H remaining. E only points to a bad node. All right, so that's good for me. I want to put the penny on E. Then my opponent is going to push it onto a bad node. Oh, and now we can use the property that I was just talking about. H leads to a good node, so H must be bad. And there we go. We've actually analyzed this full game. I've defined where the winning nodes are and the strategy. So let's say that we're playing the game and the penny is placed on H initially. It's your turn and you get to go first. Where will you go? You should push the penny onto E. That's good. Your opponent now has no choice but to push it onto a bad node. Now it's your turn. You want to put it onto F, and then your opponent has no choice but to put it onto a bad node, and then you can push it to D and you win the game. So when a game is in a graph, we analyze it this way and we talk about good nodes and bad nodes, which are really good game states and bad game states. There's a whole family of games called stone removal games, and they go like this. A game starts with, say, 10 stones in a pile. Two players alternate removing stones, taking either 1 or 2 stones on each turn. The player who removes the last stone wins. Who will win this game? Oh, and I want to emphasize, removing the last stone wins. So keep that in mind. You want to be the one to remove the last stone. So if you just think about this for a little while, and maybe you can play with a friend and kind of try to think about, what is the winning strategy? How do you know what you should be doing each time you play? It can be a little difficult to analyze, but if you write it down as a graph, then it becomes much easier to analyze. Here we go. Here is a graph for this game. So the different game states, those are the nodes, and they represent the number of stones left in the pile. So you start with 10, and then from 10, a player is going to either take 1 or 2 and turn it into a 9 or an 8. And then from there you take 1 or 2, you follow the arrows, and it turns it into a 7 or a 6. And so on. So it goes all the way down, players taking turns, moving along the edges of the graph until finally one person gets 0 and wins the game. So let's analyze this game. Let's find the strategy. And by that I really mean let's find the good nodes. Well, 0 is a good node. That game state of 0, when there are 0 stones left, that's what I want to create. By taking the last stone, I create a pile with 0 stones in it, and I win. Alright, so any state that leads to that has to be bad. I don't want to leave 1 stone or 2 stones, because then my opponent moves to 0 and wins. But look at this, 3 goes only to bad nodes, so that's good. I want to land on 3 because then my opponent has to go to a bad node. Alright, what next? How about, once I know that 3 is good, anything that leads to 3 must be bad. So 4 is bad, and 5 is bad. How about 6? 6 only leads to bad nodes, so that's good. It's good I want to put it onto 6, because then my opponent is forced to place it onto a bad node. Once my opponent puts it on a bad node, I can take it to a good node, and so on. Alright, coming back here. So we've defined 6, we know that it's good, so anything that leads to a good node is bad. So 7 is bad, and 8 is bad, which brings us to 9. And 9 only leads to bad nodes, so 9 itself is actually good. But since 9 is good, anything that leads to it, like 10, has to be bad. There we go, we've defined the winning game states, 0, 3, 6, and 9. So if you start with 10 stones, if it's your move, the first thing you want to do is remove 1, get to the state of 9. Then, no matter what your opponent does, 7 or 8, you can put the game into state 6. Then, no matter what your opponent does, 4 or 5, you can put the game into state 3. Then, no matter what your opponent does, 1 or 2, you can put the game into state 0. In fact, it's actually kind of easy to remember. These are all multiples of 3. 9, 6, 3, 0. So if you play this game, just always remember you have to create a multiple of 3 number of stones in the pile whenever it's your turn. And once you have a winning strategy, you get a sense of how this winning strategy works. Once you know what it is, you put the game into a winning state. No matter what your opponent does, it puts it into a losing state. And then you have the opportunity to make it a winning state again. And it will always go back and forth. So as long as you know the strategy and you can do it correctly, you can be guaranteed to win. So here's the official algorithm for finding good nodes. And even before this, I'll jump to the end and say good nodes, the official name for that is the kernel of the graph, or the kernel of the game. So here's how we find the kernel. First of all, number 1, circle the winning node, or potentially nodes. And then secondly, here's the repetition part, repeat until all nodes are either crossed out or circled. So A, cross out every node that points to a circled node, and circle every node that points only to crossed out nodes. Once you've done that for the whole graph, the set of circled nodes, those are your good nodes. That's the kernel of the graph. Alright, you give one a try. Say you have 13 stones, and in this game, you can remove 2 or 5 at each turn. And if you can remove 2 or 5, then you must do so. If only 1 stone remains, you may remove that 1 stone. I mean, you'd like to, right? Because then you win the game. So this is what I want you to do. Make a graph of the game, find the kernel, and say, would you rather be the first player or the second player? All right, give that a try, and then start up again to check your work. Here we go. So here's the graph that I ended up with, and I promise you, the first time I did this problem, my graph was so much messier. So it's challenging. It really is challenging to draw a nice graph the first time. So if your graph looks nothing like this, that's okay. Let's find the kernel. So 0 is the winning node, so of course 0 is in the kernel. 0 is good, so anything that leads to 0 is bad. So 2 is bad, 5 is bad, 1 is bad. So how about 3? 3 only leads to a bad node, so 3 is good. So since 3 is good, anything that leads to it is bad. So 5 is bad, and 8 is bad. All right, how about maybe 4? 4 only leads to a bad node, so 4 itself is good. So working backwards, anything that leads to 4 must be bad. So 6 is bad and 9 is bad. So cross out the 6, cross out the 9. All right, coming up to 7. Let's see, it looks like 7 only leads to bad nodes, so 7 itself is good. So anything that leads to 7 is bad. Well, that's just 9. Okay, that's already taken care of. That brings us to 11. 11 only leads to bad nodes, so 11 is good. And then 13. Oh, well, 13 leads to a good node, so 13 is bad. All right, and there we have identified all the good nodes. We've seen the kernel of the graph. Here we go. Kernel is the set 0, 3, 4, 7, and 11. Now, if you're playing this game, would you rather be the first player or the second? You would rather be the first player, because in your first move, what you'll do is you'll take away 2 to put the game into the state of 11. So there are 11 stones remaining. Once it's at 11, no matter what your opponent does, you can push it into a good node. And then after that, no matter what your opponent does, you can push it into a good node and maybe even win the game. Let's move on. The game of Nim. This is a classic game. You have several piles of stones. At each turn, you can remove as much as you want from any single pile. The person to remove the last stone wins. So it's almost the opposite game. You have several piles, and you're not restricted to a certain number that you can remove. You can remove as much as you want, but it has to be restricted to any one single pile. Here's a little demonstration online that's pretty nice. All right, so in this applet, I can click the restart button, and it sort of randomly generates piles of stones that are drawn vertically. Here we go. So for example, let's say I have 7 piles of stones, and so I can, let's say in D pile, I want to remove 3 stones, so I'll click here. So I remove 3 stones. And then the computer removed several stones from pile B. I can remove as many stones as I want from a pile. I could even remove the whole pile. So how about pile C? I'll just take all those stones away. The computer removed some stuff from F. I'll remove 1 from G. The computer removed 1 from A. I'll remove 2 from D. The computer removed some. I'll remove these. I'll remove E. The computer removes F. And the computer wins. All right, let's try one more. See if I can beat him this time. All right, I'll remove 2 from C. How about 3 from D? I'll do 2 from B. How about I'll remove the last stone from C? Okay. Can I win? I don't think so. I remove it from B. He removes A. He wins the game again. He's good. What is he doing? What is his strategy? Okay, let's take a look at some strategy for Nim. So 2-pile Nim. Let's analyze that. What is your strategy if one pile has 4 stones and the other pile has 3 stones? So 1, 2, 3, 4. 1, 2, 3. So there are a lot of different game states. In fact, with 4 piles, in a pile with 4 stones, there are 5 game states. I can have 4, 3, 2, 1, or 0. And in the second pile, there are 4 possible states, 3, 2, 1, or 0. And so as a combination, I have 5 times 4. I have 20 different game states. And so in fact, we could see them this way, as a grid of points. And so pile 1, the size of pile 1 is represented horizontally, and the size of pile 2 is represented vertically. And we start at this top left corner where pile 1 has 4 stones, pile 2 has 3. And I want to get to the game state at the bottom right. So these are the nodes of the graph. These are the game states. What are the edges? Well, I can move to the right. I can take away 1 stone from pile 1, or I could remove 2 stones from pile 1, or 3 stones, or 4 stones. And if I was at this node, 3, 3, I could remove 1, or I could remove 2, or I could remove 3. Or if there's only if there are only 2 stones in pile 1, I could remove 1 or 2. And you can see that there are a lot of edges. If I remove stones from pile 2, I can remove 1 or 2 or 3, and there are lots and lots of edges. So what we'll do is, I'm not going to draw the edges in there, but we'll just know that they exist. They allow me to move any amount to the right or any amount down that I want. So let's find the kernel. The bottom right, that's my winning node. And how do I get to that winning node? I can move down from any position, or I can move right from any point to the left. So remember, any node that leads to a winning node is in fact bad. So all of these nodes above that guy are bad, and any node to the left is bad. So I will just X all of those out. Now can you see where the next good node is? It's right at 1, 1. Because from here, I can only go to bad nodes. So 1, 1 is a good node. Oh, which means that all of those above it are bad, and all of those to the left are bad as well. So the next good node, look at that, 2, 2, that's good. Anything above it is bad, anything to the left is bad. Now 3 has to be good, because it leads only to bad nodes. And so 4 is bad. So my winning strategy looks like to go right along this diagonal, which basically means keep the 2 piles the same size. NIM with 3 or more piles is pretty difficult to analyze, but there is a winning strategy that we can describe. I mean, you can imagine with 3 piles, we're really talking about like a 3-dimensional array of dots, or 4 piles, 5 piles. It really becomes unmanageable very quickly. Okay, there are 2 things that we need to know in order to figure out this winning strategy. First, the direct sum of binary numbers. So I have a couple examples listed here. The big idea with the direct sum is that 1 direct sum 1 equals 0. Ones just cancel each other out. And that's what I have on this first column here. 1 plus 1 is 0 on the bottom. Now other normal addition happens. 0 plus 0 is 0. 0 plus 1 is 1. But anytime I have a pair of 1s, they cancel each other out. In fact, not just a pair of 1s, but if I had 4 1s, 1 plus 1 plus 1 plus 1, that would also equal 0. Or if I have an odd number of 1s, so take a look. Here, if I have an odd number of 1s, then the answer is 1 on the bottom for the direct sum. It's like I have a pair that cancels each other out and just makes 0, and then there's a 1 left over. So if you see an odd number of 1s, the solution is 1. Their direct sum is 1. If I have an even number of 1s, the direct sum is 0. So I have an even number of 1s, answer is 0. Odd number of 1s, the answer is 1. Odd number of 1s, the answer is 1. All right, so that's how a direct sum of binary numbers works. The second thing that we need to know is basically, what binary numbers, what are those? So a quick tutorial on writing numbers in binary. The first thing I do is write some descending powers of 2. So I don't know, maybe start with 64. 64, 32, 16, 8, 4, 2, 1. Those are the powers of 2 getting smaller. Now, if I want to write the number 5 in binary, I need to figure out which powers of 2 do I add to make 5. So I sort of scan to the left. I find the first number that's less than or equal to 5. Oh, there's a 4. I'm going to put a 1 there. I'm gathering together the 4 and the 1. 4 plus 1, that's 5. So I don't use any of the 2's. So the binary number for 5 is 101. It gathers a 4 and a 1 together to give me 5. How about 13? So I scan across until I find something less than 13 or equal. 8, okay. So 13, I've taken care of 8, so now I need 5 more. So there's a 4 here, so 8 plus 4, that's 12. Oh, I just need 1 more, 1 there. So my binary number for 13 is 1101. Oh, what you think about it is really that initial 8 plus the 5 that I found before. So 8 plus 5 is 13. How about 17? I come across, oh, I see the 16 and the 1. So 16 plus 1 is 17. And then I just have a bunch of zeros in between. So 1, 0, 0, 0, 1. That's the number 17 in binary. And then 27, let's see, how about, where do we go? We go to 16 first. 16 plus 8 is 24. So now I'm up to 24. I need 3 more. So how about a 2 and a 1? There we go. So 1, 1, 0, 1, 1. That's how you write the number 27 in binary. Okay, now we're ready. We've got direct sums and we have binary numbers. Now we can talk about our winning strategy for NIM. To determine the winning move in NIM, write the size of each pile in binary and find the direct sum. Then, take away enough stones from one pile so that the new direct sum will be all zeros. Okay, here's an example. Here's how we do this. For example, say we start with a 13 pile, a 9 pile, a 7 pile, and a 5 pile. How many stones should you take? From which pile? So, first thing, let's convert 13, 9, 7, and 5 into binary and find the direct sum. So there it is. So the direct sum of those 4 numbers in binary is 0, 1, 1, 0. Now, in the sum, identify the leftmost 1. So here we go, there's my leftmost 1. It's in the second position from the left. Find a binary number above it that has 1 in that position. Oh, okay, so actually I have several choices. 5 works, 5 has a 1 in that position. The 7 has a 1 in that position. Not 9, that's a 0, and the 13 has a 1 in that position. So I could choose any 3 of those. So just to move things along, let's say I'm choosing the number 13. So in that number, in the 13 that I've chosen, change every bit that lies above a 1 in the sum. All right, this is kind of complicated, right? So in the sum, the ones are in the middle 2 positions. So in the number 13, I'm going to take those middle 2 positions and switch them. Or, the 1 turn it into a 0 and a 0 turn it into a 1. Okay, and so when I do that, the 13 becomes this new binary number. What is that new binary number? Can you see? Let's see. Maybe I'll write above it the 1, 2, 4, 8. So 8 plus 2 plus 1, that looks like 11. That new number, 11, that's the number of stones that should remain. Look at this. When I make 11 instead of 13, now when I take my direct sum, it all becomes 0. So that's what I wanted to do. And that's the winning strategy. Whenever you have several piles of stones, figure out how you can remove stones from some pile so that the new direct sum is 0. Why? Why in the world do we do this? Why is that the winning strategy for NIM? Because this game state, when I'm able to make the direct sum into all zeros, that game state is in the kernel of the game. Now, what are the defining characteristics of the kernel? Right, that if a node is in the kernel, then anything that goes away from it is not in the kernel. Or if I'm in a position that is not in the kernel, there's some edge that leads to a position in the kernel. And let's see how that works here. Anytime the direct sum contains ones, so it's a bad node, it's a bad game state. Anytime the direct sum contains ones, there is a move you can do to force the sum to equal 0. So anytime I'm in a bad position, I can move to a good one. On the other hand, if the sum is 0, like what we see on the top right, if the sum is 0, then any subsequent move must cause the new direct sum to contain 1s. Because anything you do from this point, if I change one of those piles, change one of those numbers, it's going to introduce some 1s down below. Alright, so you try this. Find the winning move if the pile sizes are 13, 13, 9, and 2. Give it a try, see what you can do. Alright, here is the solution. So 13, 13, 9, and 2, this is what they look like in binary. Here's their direct sum. I find the leftmost 1, and I select one of those numbers up above. So either the 13, 13, or the 9. Let's just say the 9 in this case. Where are the 1s in my sum? It's the first, third, and fourth position. So first, third, and fourth bits get changed. So that turns into 0, 0, 1, 0, and the new number is 2. So I started off with 9, I want to make 2, so I will remove 7 from the 9 pile. That's just one possible winning move. In fact, I do have others. What would have happened if I had chosen 13 as my number to change? So I need to change the first, third, and fourth positions, which makes a new number 0, 1, 1, 0, and that is the number 6. So this 13 would change into a 6, which means I need to take away 7 from the 13 pile. So I can either take away 7 from the 13 pile, or I can take away 7 from the 9 pile. Either of those would be a winning move. Alright, the game of Nim. It's a classic game with a crazy winning strategy. I will stop here.